Great. Yeah, great. OK, we have the last speaker of the session, who's Hejing Lee, who's a PhD student, first-year PhD student, right, at Max Planck Institute for Software Systems. And she's going to talk about basically modular network simulation. Thank you.
Hello, I am Hejing Lee from Max Planck Institute for Software Systems. Today, I'm really excited to talk about SimBricks, a simulation framework which enables end-to-end network system evaluation. This work is in collaboration with Jialin Li from NUS and my advisor, Antoine Kaufmann. So full system end-to-end evaluations in physical testbeds are essential in network systems. Typically, we care about overall system behavior, such as throughput and latency. And many factors in individual components affect overall system performance in very complex ways. For example, the CPU cache latencies, NIC processing time, or switch queuing delays. And these hardware components have complicated interactions between them, and thus make the end-to-end performance hard to predict a priori. However, evaluation in physical testbed is often not feasible. Much recent work requires cutting-edge hardware not yet available at the publication time. For example, in this in-network system called in-network processing system called NOPaxos required programmable switches, which were not widely available at the publication time. So without the actual device, the authors used network processor for their evaluation. It can emulate the functionality of the programmable switches, but incurs latency and bandwidth overhead. Other work proposes extensions to current hardware or entirely new ASIC designs. But because of the long design and manufacturing cycle and cost, physical testbeds are out of reach for most of the researchers in this space. To make things even worse, we often need testbeds with tens or hundreds of our proposed devices. When a physical testbed is not available, simulation is a common alternative for evaluation. And there are outstanding simulators available. Computer architects often use host simulators such as QEMU or Gem5 to simulate individual computers, including the CPU or other devices. Hardware designers might use Verilator or Vivado to test hardware designs during development. Likewise, NS3 or Omnets are used for simulating network topologies and protocols. However, none of these actually simulates the full end-to-end system, and thus can only deliver a piecemeal evaluation. Since we already have simulators for all the components we need, it's natural to ask whether can we combine and compose them to simulate a full end-to-end system. And in the rest of this talk, I will show you how we enable exactly this with our system, SimBricks. Specifically, SimBricks combines host, hardware, and the network simulators into full end-to-end network simulations. Thereby, we want to enable the following. First, run and evaluate unmodified hardware and software system implementations. Easily use different combinations of simulators for different tasks, especially as each simulator has a different trade-off between accuracy and the simulation time. Use SimBricks to simulate sufficiently large network systems. And finally, make it easy to integrate other old and new simulators. So before diving into the technical details, let me show you a concrete example illustrating what that might look like. Suppose we are trying to evaluate the NOPaxos in-network processing system. Here, a physical testbed consists of 3 servers and 1 client that all connected to a programmable switch. The switch is programmed to number all the packets from the client and broadcast it to all the servers. We realize this testbed in SimBricks as follows. We use Intel's Tofino simulator for the network, connected to the servers and the client. Each server and client consists of an instance of an Intel i40e NIC simulator and Gen 5 as the host simulator. Then, in the host simulator, we run the modified operating system and user program. For the switch, we also run the same modified P4 program as in the physical testbed. To get the accurate performance numbers, we configure all the simulators as synchronized. To achieve this, we have to overcome 3 technical challenges. First, there are no interfaces for connecting simulators together. Specifically, to enable modular composition, we need common and well-defined interfaces between simulators. Second, as many simulators are already slow, naively combining them further slows things down because of overheads for communication and synchronization. In particular, we need efficient and scalable synchronization of simulator clocks. Third, simulators have different execution models. For example, Verilator is simulating hardware cycle by cycle, and NS3 is asynchronously scheduling events. How can we combine such mutually incompatible simulation models? To enable modular combination of different simulators, we define standard interface between types of simulators. These interfaces are based on natural boundaries in physical systems. More specifically, PCIe interface between the host and the hardware simulator, Ethernet interface between the hardware and the network simulator. To integrate a simulator into SimBricks, all a user needs to do is add an adapter which implements the component interface without modifying other parts of the simulator. So far, we already integrated several well-known simulators. Please find out our paper for the full list of simulators. For scalability and ease of integration, we run individual simulators as separate processes on parallel cores and let them communicate by passing messages through pairwise optimized shared memory queue. Message passing also aids with integrating incompatible simulation models, as we treat the simulator as a black box and only need to implement our interfaces. Since the simulators communicate by passing messages, we can also naturally scale across different physical machines. To do so, we implement network communication proxies that forward messages from and to shared memory queues over TCP or RDMA. Later in this talk, I will show a concrete example of how to use this. Simulators running in parallel naturally proceed at different rates. Therefore, time synchronization is required to obtain meaningful performance. In SimBricks, we design an accurate and scalable synchronization mechanism that relies on message passing. We tag each message with a timestamp, indicating the simulator time when the message is to be processed at the receiver. Our synchronization protocol then ensures messages are processed on time. SimBricks simulations reflect the physical structure of the simulated system. Specifically, each simulator only communicates with its directly connected peers through the links incur a configured latency. We thus only have to synchronize the peer simulators, and the latency provides some slack. Please refer to our paper for more detail about the synchronization mechanism. We have done an extensive technical evaluation in our paper. For this talk, I will focus on 2 things. First, I will show 2 concrete use cases for using SimBricks for software and hardware system evaluation. Second, I will demonstrate that SimBricks can simulate large-scale systems. Let's revisit our NOPaxos example for earlier, and look at how SimBricks can serve as a virtual testbed for evaluation. We use the same configuration as mentioned before. To keep simulation times lower, we configure host simulators as single-core machines with simpler in-order processors. The goal here is to convince you that SimBricks simulations can be useful, even if they do not exactly match the physical testbed. Detailed validation of component simulator parameter is orthogonal to what SimBricks wants to achieve. Here on the left side is throughput latency plot from the original NOPaxos paper. The x-axis is the request throughput, and the y-axis is the median latency. The three lines shows different system configurations. And on the right, the same graph obtained from our SimBricks configuration. Although we did not validate or tune individual simulator parameters to match the physical testbed the authors used, still, SimBricks can reproduce the general shape and the relative differences. Second, we show that SimBricks can offer an end-to-end testbed for hardware designs. We show this with Corundum, an open-source RTL NIC implementation. Here, we use the unmodified Corundum hardware RTL simulated in Evaluator, and run the unmodified apps, operating system, and drivers in the Gen 5 as a host simulator, combined with NS3 as a network simulator. For performance evaluation, we enable synchronization in all the components, while for interactive testing, we can disable synchronization and use QEMU with KVM. Finally, I want to show you that SimBricks is capable of simulating large systems. Here, we simulate a hierarchical topology with racks connected to a core switch. Each rack comprises 40 hosts and a TOR, and we distribute the racks and the core switch to separate physical machines. Each top of rack switch connects to the core switch using a SimBricks TCP proxy pair. We vary the number of simulated racks from 1 to 25, resulting in 40 to 1,000 simulated hosts. As you can see, the simulation time increases only moderately, particularly for Gen 5 as the slowest component simulator. We see only a 14% increase as we scale the number of simulated hosts and physical test servers. We conclude that SimBricks scales to simulate large network systems. To conclude, I've introduced SimBricks, which combines component simulators into a full end-to-end system with meaningful performance results. And we can simulate unmodified software and hardware systems. SimBricks is open sourced, and we are actively maintaining the projects. And we'll be happy to hear from all the potential users. Thank you for your attention.
Thank you very much. Questions on SimBricks? Work your way up. There's a question behind you at the back.
Hello, Mark Handley. So when we're running large simulations, we're often running much, much slower than real time, especially if you use things like NS3 to run a large simulation. How do you handle slowing down things like the operating system's TCP retransmit timer or other timers that you might have in your NIC stack or things like that?
Sorry, could you please repeat the question?
OK, so when you're doing a reasonably large network simulation, you often have to run slower than real time. Yeah?
Yes.
But you're using the real operating system, which therefore has real-time timers, and you're running your real NIC stack, which will have real-time timers. So how do you slow those down?
Well, if you are using the, so first, thank you for your question. So if you are using the simulator that is using its local time and synchronized, then it's actually not operating in a real-time manner. The simulator time is simulated inside the simulator.
So it might not catch those perfectly. But it might be a longer coffee time discussion, because there's a man who spent many years doing serious simulations. Yeah. Any other questions? Ooh, sorry, I'm getting feedback. Yeah, one more. Please make sure you do catch Mark for coffee break.
Hi, thanks for the talk. This is Thomas Calvert from AMD. My question is, have you considered and do you support hybrid execution environments? So, for example, instead of using a simulator for the network stack, you could plug into the real network at this point, because maybe you're not interested in simulating that bit. I'm thinking in particular for runtime, it might be faster.
Yes, thank you for your question. I think you're asking about why not using emulation when you need to, when you don't need to simulate the real time.
Yeah, you could still run an end-to-end test, but not simulate all the components. Use the real components in place of some of them. Mix and match.
I think the question is if one of your bricks can be an actual, I don't know, like instead of QEMU or something.
I think if you have the network emulator in hand, you can definitely plug in SimBricks and use it as an emulator instead of cycle-accurate simulator for the network.
Okay, thank you.
And I think the broader answer is that this is an open source project, so hopefully the community can continue contributing. Any other questions? Great. Well, let's thank the speaker one more time. Thank you very much. Cool. You just have over 20 minutes for coffee before we start the keynote. Live from Deborah. Thank you very much.